Good morning, everyone. My name is Ping Yang. Today, my presentation is about a Centaur system for assisting human working with load carriage. Working with load carriage is a common task in our daily life, disaster rescue, and medical disinfection activities. There are some devices have been proposed to alleviate humans' load carry, such as suspended backpacks, exoskeletons, and super robotic legs. Although the suspended backpacks can optimize the distribution of the load force on human body, it still needs human to bear the whole load. As for the legged exoskeletons, the rigid structure can transfer the loads to the ground. However, it is inevitable to interfere with humans' natural locomotion. As for the super robotic legs, different from the exoskeleton, super robotic legs are kinematically independent of human legs. Thus, it can avoid the physical interference with human natural limbs. However, these robots will cause the additional twisting interference, which may increase the human energy consumption. And as we all know, the quadruped has the great ability in the low carriage, such as the horse and camels. Based on the concept of the SRLs and the quadrupeds, we have proposed a novel robot, the Centaur robot, just as shown in this figure. The Centaur robots have the advantage what we just talking about, such as the relieving human load carriage and little interference with the human locomotions. What's more, this structure has placed backward of the user can largely increase the stance polygons, and it can therefore increase the working stability. And the mechanical design of the Centaur system largely maintains the intelligence and motion dexterity of the biped, with the strong environmental adaptability of the quadrupeds. This Centaur system consists of 3 parts, a backboard, a spine structure, and 2 robotic legs. The backboard can connect the human body and robot mechanism, and the spine structure is designed to place the whole loads and the electric elements such as the battery, the sensors, force sensors and MU sensors, and the controller elements. And the 2 robotic legs are mounted on the spine structure, which is designed to transfer the low weight to the ground and can release the human's load carriage. As for the control system, we can know that the Centaur system is a human-robot mixed system. Humans' influence and interactivity need to be fully considered, such as the force and motion. Therefore, the human-robot interaction force have been included to coordinate the robot locomotion, just as shown in this whole control structure. We find that according to the gate scheduler, the human robots can determine the robot whether in stance or swing phase, and the leg motion control will be generated by this stance or swing-based trajectory planner, and the desired trajectory will be sent to the actuators and make some locomotion. This is the experiment of our Centaur system. We have text is compliant motion control. As shown in this figure, the subjects move forward and backward to test whether the robots can move accordingly to the human motions. And when the subjects move upward and downward to test if the Centaur can move accordingly according to the posture, just the pitch angle. And this is the mixed task, both the force and posture tasks. And we have also tested the strength length adjustment function for this system. As the force increase, the system will control the legs to stride a large step to coordinate the human locomotion. And if the force decreases, the step length will decrease too. And we also conducted some experiments to test the load carriage functions. The subject was asked to varying the loads in 3 situations, just working without any loads, and working with loads with a backpack, and working with our Centaur robot on a terrace. And from the result, we find that the Centaur robot can effectively assist the human walking to reduce the load by 60%. We also have conducted some experiments to validate the Centaur robot working with human locomotion. The subjects can work on level ground wearing the Centaur robot, just as shown in these 2 videos. Even though this structure and system are just in a very low speed, but it can greatly coordinate the human locomotion. Okay, make conclusions. In this paper, we have proposed a novel system to assisting human working with load carriage, the Centaur robot, and a control strategy also have been proposed to make the robot motion control appliant to the human. And experiments also have conducted to validate these concepts. In the future, we will generate the design interaction force and apply it to the control system. And we also will optimize the Centaur robot's mechanism to improve the load carriage performance. This is the end of my presentation. Thank you for your listening.